Hello, welcome to the System Units Notes, Video 1. In this unit, I want you to be able to tell the difference between a system and an object. I want you to understand the difference between inertial and gravitational mass. I want you to understand what a force is and its effects on objects. And I want you to explain why forces come in pairs within a system. So, we need to start by talking about systems. And really everything can be considered a system. What it is a collection of objects, and then the objects themselves have no internal structure. So really, everything can be thought of as a collection of objects, um, right down to the smallest building block, something what we call an atom. So looking at an atom, for a long time, atoms were thought to be indivisible. They were thought to be the smallest unit of matter. So, you know, everything is made of atoms, so everything would be a system. And then in the early 1900s, we started learning that, well, no atoms have internal structures themselves. So even an atom can be considered a system. And so when we take a look at a system, we need to determine what are the objects within the system. So going back to the atom, there are three what we would call objects within the atom. We have the protons, neutrons, and electrons. Now, the properties of the objects help determine the properties of the system. So, for example, the number of protons will tell us what atom it is. So, for example, one proton would mean hydrogen, and two protons would mean helium, and three protons would mean lithium. The neutrons will tell us what the isotope it is. And the number of electrons tells us what ion it is. And for a long time, we thought that, protons and neutrons and electrons were the smallest things there are. We thought that those were objects. And, well, we started learning differently that, even these things we call objects are made of smaller objects. Um, we would call this whole process of finding the smallest thing out there is called particle physics. What is the smallest thing out there? So some of the protons we found out are made up of even smaller particles, more fundamental, which we call um, quarks, and uh, electrons. It turns out are about the same size as a quark, maybe a little bigger, but electrons we found were elementary. So electrons, there we have not found any internal structure to an electron. And protons and neutrons we found do have internal structures, and we call those quarks. And so far we have not found any internal structure to a quark. So everything is made up of quarks and electrons. And there are a few more fundamental particles that are more exotic. So, you know, we need to have a stopping point. I mean, we can't, go down to the electron and quark level every time we want to analyze something. So when can we refer to something as an object or a system? And what it comes down to is properties. So we consider a system an object when the properties of, the objects inside of it are not important to modeling the behavior of the system. So, as an example, if two cars collide, we really don't care about all the atoms in each car. Um, so some other examples. Well, a planet. A planet is obviously a system made up of smaller objects, but when the planet is within, let's say, a solar system, we can treat that planet as an object because, you know, the weather patterns on the surface of a planet doesn't really affect its orbit as it goes around um, its star. Another example, gas particles. Um, and this one can get a little tricky because we do want to consider it a system when we're dealing with temperature because the kinetic energy of the particles of a gas determines its temperature. But in some cases, we really don't care about the individual particles. Okay, so moving on. Now we need to talk about mass. So systems and objects have properties of both inertial and gravitational mass. And mass can be kind of tricky. After taking chemistry, you may think you know what mass is, but the truth is we really don't know what mass is. But we can find out its properties. So first off, inertial mass. So the inertial mass is a property of an object or system, and it determines how its motion changes when it interacts with other objects or systems. Um, think about, it's harder to shake a larger object than it is a smaller object, and that's because of its inertial mass. So larger masses are harder to accelerate. Gravitational masses. So this is a property of an object or system that determines the strength of the gravitational interaction. Whenever you see the word interaction, you can think of like a push or a pull, kind of like a force. And it's with other object systems or gravitational fields. So uh, larger masses would weigh more. So far, all experimental evidence tells us that inertial mass and gravitational mass are the same, which is kind of interesting. So really what it comes down to is how we take the measurement. We measure inertial masses by trying to accelerate objects, and we measure gravitational mass by weighing objects. Now, forces. What exactly is a force? A force, I consider a force an interaction between two objects. And so far, for physicists, we have identified 4 different interactions. And then from the strongest to the weakest, we have the strong nuclear, the electromagnetic, the weak nuclear, and the gravitational. So, strong nuclear. Um, it holds quarks together. If you think about the nucleus is comprised of protons and neutrons, so things that are positive and things that are neutral. And positive repels positive, and neutral could care less, but for some reason, that stays together. And if you really think about it, it shouldn't. All the protons should repel each other. The nucleus of an atom should just fly apart, but it doesn't. And that's because protons and neutrons are made of quarks, and the strong nuclear interaction holds quarks together. Now, this is a very short-range interaction. Some atomic nuclei are too wide for this force. So it's a very, very, very short-ranged interaction. Next, we have the electromagnetic. Sorry about that. Better change it. Holds So the electromagnetic interaction will hold oppositely charged objects together, or if the objects have the same charge, push them apart. And what's kind of cool is that this also works for magnets. It holds oppositely magnetized, so north versus south, objects together, or pushes the same magnetic poles, north-north, south-south, apart. And this will obey an inverse square law. We talked about relationships in the previous unit. This is one example. This interaction is proportional to 1 over the distance squared. So as the distance between the charges separate, the force becomes weaker with 1 over that distance squared. Next, we have the weak nuclear interaction. This one is a little tricky. Basically, it's responsible for protons decaying into neutrons and neutrons decaying into protons. So we have beta decay, in which a neutron decays into a proton and an electron is emitted. And then finally, we have the gravitational interaction. Gravitational interaction is the weakest of the four, but it's a very long range force. So this force holds objects with mass together. And again, we really aren't sure why. We can measure the effects of gravity, but we don't really understand what gravity is. Gravity is so strange that it even affects time and light. So gravity is really, really cool. Just like the electromagnetic, this is going to obey an inverse square law. So the gravitational force is proportional with 1 over the distance squared. So as distances between two objects grow, the gravitational force pulling them together becomes weaker with 1 over the distance squared. All right, this finishes video 1.